Hey guys, Angel here, and right now we're going to be going over question 3 for the chapter 3 practice RQ. And so the question asks, use the table of energies provided to calculate the strain of the highest conformation of 2-bromopropane looking down from C1 to the C2 bond. Okay, and so first thing we have to do is we have to draw out our 2-bromopropane, which I've done here for you. And then it wants us to take a look at this from the C1 to C2 bond. So this is my best attempt at a little eye that is looking at this bond down to that bond. And so that's what these drawings are. But first we're going to go ahead and go over the different energy conformations that you can have and how they each result in a different torsional strain and potential energy. So this is just an example I stole off the internet. And the first example, well, first let's see what compound we're looking at. And so we've got a carbon here that's attached to our back carbon, which is the circle in the back. And so that would be both our carbons. Now we just want to make our attachments. And we have a methyl group. And then in the back you can see that second carbon has another methyl group. And so we're actually looking at a butane. The other connections are just hydrogens, so we don't need to add anything else. And so this compound that we're looking at is butane, and so the butane can take 4 different energy conformations. The very first one is fully eclipsed. Notice that there is another eclipsed, but this one is fully eclipsed because the 2 largest compounds are right on top of one another. There's zero angle of rotation on the 2 largest compounds, which are the methyls in this case. And so then we just keep going forward, whereas if we were rotating just one of them 60 degrees each time. And so this next conformation, the Gauche conformation, also known as a staggered, has a 60 degrees rotation, and that would actually have less potential energy because there's less of a torsion strain due to the difference in angle that is between there. Remember, we don't want bigger molecules too close to one another. And then we just keep moving on forward. The eclipsed would, notice how they're again right on top of one another. However, this eclipse is different from fully eclipsed because the 2 largest compounds are not on top of one another. And so there's less energy in that than there is in the fully eclipsed. And lastly, we have the anti, which is going to be our lowest energy conformation. The anti, that is when the 2 largest compounds are farthest away from one another, which is going to be 180 degrees. If we were to keep going this way, we do not go to 240 degrees. Instead, we start going down. We'd go back down to 120, and that's because if we were to put the methyl here, that would not be a 240 degrees, that would just be a 120 degrees that way. Okay, so now let's go back to our problem. And so it wants to know what would be the highest energy conformation for this compound. Well, we can only actually take 2 conformations in this compound because we have a CH3 here, so that has 3 hydrogens, and then this second compound, carbon, has 2 hydrogens and 1 bromine. So in these drawings you'll see that regardless of how much we were to twist this bromine, we'd always either have a CH3, a methyl, and a hydrogen a methyl and a bromine in the gauche position, or a methyl and a bromine in the eclipse position. So then once you've determined that, and just for perspective, this is our first carbon, and then our second carbon is the back carbon. This last carbon over here, this methyl group, is represented by CH3 right here. And so hopefully you can see that as if you were looking at this eye angle from this first carbon to the second carbon, how you would see each one of those in this perspective. And so now the highest energy conformation, remember, that's going to be the eclipsed versus the gauche. So the eclipse is the highest energy conformation. So now all we have to do is figure out how much energy comes from each eclipse that is happening. And so we have 2 hydrogens that are eclipsed, so we've got 1 bromine and a hydrogen eclipsed, that's 1.5, and then a metal and a hydrogen eclipsed, and that would be 1.3. So when you add all those together, you get 3.8.